We are operating systems and we're looking at virtual memory. I want to start with one of the programs. Let's see. We're running in xv6. Let's pick one of the programs. Memory. What is memory? Okay, so this is one that prints addresses, and we have different types. So let's just see, we run it to see what those addresses are. Okay, so these are all sleeping forever. Okay, that's good. I'll kill that. All right, these are all 32 bits of address, which means the full address would be filled with zeros. So these are all virtual addresses. Examples. So we have main is like that. We have a global. So a global variable, an example from this program is b78. We have the stack. Somebody remembers that's 2 FEB, and the heap, AFF0. Okay, so let's take this heap one. What happens in hardware is this is not directly sent to the memory controller. It's split up into its 32 bits. So what's A in binary? 1010. F is. All right, so that's what it is in binary, and the rule is the first 10 bits is index into page directory. In this case, what are the first 10 bits? Zeros. I'll just underline those to separate them. So that's a 0. The next 10 bits is index in page table. The next 10 bits is this. I'll italicize those. So what is that? It ends in A. That's a 10. And then the last 12 bits is an offset in a page. And for that we have this, whatever that is. So F0, we need to convert it to decimal. Sorry, the last 12 bits. So it would be these two as well, which means 2F0 is what we need to convert.
It's the last 3 sets of 4.
752? It's okay, got it. Yep. The last 12 bits. All right, so you've got FF0, which is 4080. Okay, so what would happen in hardware when this memory address, when we try to access this memory address, the order of operations is go to the process's page directory and get the 0th entry. So the 0th entry gives a memory address, a physical memory address a page table. So go to that page table and get the which row out of the page table. 10, the 10th row out of the page table. Okay, that 10th row has a physical memory address of a page. Go to that page and get the 4080th byte. Okay, so a page is 4096 bytes in x86. All right, so question is, if we don't have any help from the hardware, how many memory accesses is this? So this is a discussion question. You can look at that and think. You can also look at, let's see, the picture. This picture. So this is a picture of that happening. So there's the picture, and we have the description here. Let's do this so we can have both on the screen. That's pretty small. Right. So the question is, how many memory, just to read one variable, 1 byte, how many memory accesses does that take? All right, ready, set, think, and discuss. Okay, so we're asking how many memory accesses does this take? Hopefully 1 normally. With caching, so we'll say what happens there in a second, but without caching. However you spell accesses. All right, so what are the things that we need to read? Let's go over to the picture. So we start with, this is the address itself, and let's say that we don't have any memory accesses to just have the address sitting there. The address is already sitting there in the CPU or something like that. So then we have 10 bits out of there to point to this row, and then we need to read this, right? So we definitely have to read this entry in the page directory. That has to happen for sure. That's 1. Then the 20 bits there gives the address of a page table. And so what we're going to do is we're going to take that 20 bits and put on this 10 bits, and that gives us an entry in the page table that we need to read. So we're definitely going to have to read this one as well. We have to read this to get this arrow, right? This arrow comes from this page directory. We want to get this as well, so we definitely have to read that. And then we definitely also need to read whatever the actual item is. So I think 3 is the best answer. And whether we want to count more depends on whether doing this arithmetic stuff is a memory access. But the first approximation answer is a read of the page directory entry, PDE, a read of the page table entry, that's this thing, and then a read of the actual address we want. All right, so you're adding other arrows, Joe, I don't know. I think 3 is the right answer. I mean, it's actually, this is a 32-bit thing, so we're reading a 32 bits there. So first we have 32 bits sitting there that gives us a virtual address, and then we have 32 bits that we read here, and we have 32 bits that we read here, and then we have 1 byte. Right, once we have the physical address, we maybe read 1 byte. So depending on how we want to count that. So this is a 32 bits in our system, and this is 32 bits. And then this is like 1 byte, or maybe we're going to read or whatever, right? However many bytes we're going to read there. All right, that's bad for performance. If every time you want to access a variable, you're actually going to have to do 3 reads instead of 1. So that's what the TLB is for. That's bad. So we'd have like a 3x performance hit or something. So the TLB is the translation look-aside buffer. Let's say that's correct. That's my TLB. So the TLB is going to keep like this entry here and this entry here in cache, which is faster than memory. So you'd have like 2 cache hits and a memory access in the good case. So with if the TLB keeps the PDE and PTE in cache, then you have cache reads for that, and 1 memory read. Anybody remember off the top of your head how much faster is cache than memory?
10 times.
Something like that. Let's just say 10 times. Right. So let's just pretend it's 10 times. It depends on the CPU. So if your cache is 10 times faster than memory, then your using virtual memory costs you like 20%. Right, because you'd have a 1/10 to read this cache entry and a 1/10 to read this cache entry memory. So it's like 2/10 extra. So the details of how that actually works out depends on the CPU, and I don't know. I'm not an architecture person about what the actual performance hit is. Somebody could look that up if you wanted to. That's a good thing for your architecture class. Okay, so that's one. This stuff here, I'll say, hey, this is classic interview question type stuff. So if you've done operating systems, then we assume that you can do this type of, right? How many reads does it really take to do virtual memory? Questions? Let me do this. So questions about caching and virtual memory. What's the real performance hit? How often do you have cache misses? So cache miss would be somewhere in hardware. There's going to be circuitry that when you're trying to read a memory address, it goes to its cache first for these entries. And so how often in the real world do you miss the cache? And that depends on your program or whatever, but there's some statistics on that. So some of these answers are in the O-Step book. If we read in there about virtual memory, and I did it a couple years ago, I read that, and I haven't read it this year. So if you want bonus points or something, anytime you're done, you can go through our list of things that we're supposed to come back to that we probably won't, and find out the answers and come discuss with me, and then you can be the one to present it to the class. Okay, other questions? Let's go to looking at what we're supposed to do in the homework assignment, because it's pretty interesting. And I will be able to give you something, we'll decide on a starting point. Okay, so let's go back to homework 3A. This is well defined, I think. You're supposed to do a system call, and you're supposed to have a program that works, and Joe thinks that he has one that works, but I'll show mine. Well, I'll show it running. which one? XV6. All right. Right. All right, so you're supposed to end up with a free program that runs and produces this. This is part of homework 3B, but for part A, you have a system call. Inside of there, you have the number of processes, and it talks about where you're going to get that from over here, I think. The size of user virtual memory, UVM is user virtual memory, and this is added up for all processes, and then the number of CPUs. And where's that information coming from? Right, so if you go to proc.h, there's this. So every process has one of these, and there's a size. So we want to go through all the processes and add up the size. And so then we need to get a list of all the processes, and that is a variable somewhere, proc.c, ptable. So there's something called ptable that if you, like if I'm in proc.c, I could say in the code, and inside of one of the functions, I could say ptable.proc bracket 0. And then I only want to look at processes that are actually, real processes and not just, dummy stuff that's not running. So we look at the state, and the state can be, these are the choices for what the state could be. I was adding up everything that's not unused. If it's unused, then that's just an empty entry in the process table at the moment. Okay. So you need the ptable variable, and you need to look at the proc to get the size of virtual memory and the number of processes, right? Okay, what about the number of CPUs? Somewhere, n CPU. So there's something called n CPU that's declared somewhere. You can find where it's declared. So np.c, okay, it's an integer, so then if you're going to use it in some other file, you need to have in your file declared extern int and CPU. You're not declaring the space here, you're declaring that you're going to use somebody else's. Okay, let me pause. All right, moving on to virtual memory. I'll show you what my 3B looks like. Not that. And I'm going to give you some part of this. Let's see, we'll show it first, and then we can decide what you actually need. Okay, so I added to my free.c. So I had the system call to do system load, right? You're going to have something like this. You have a system info structure, you call the system load. This is from homework 3A, and then you're going to print the stuff. So this part is like homework 3A. If you haven't finished it, then that's part of it. And then this would be and homework 3A. So I'm just adding on to this free program for homework 3B in terms of the user part of it. Okay, so for the user part of it, I have options. So so if I run free, it prints the stuff that was there before, but then it also says if you do free-usage, then these are different things that could be done. We have the -h from the homework 3A. Then we have really two different virtual memory things that are cool. One is tracing the you know, breaking down a virtual memory address into all the different parts in the code. Like, here's the first 10 bits. So here's the first 10 bits. There's the next 10 bits. And then what are the addresses that are getting passed around here? So that's one thing. And then for the pointer, I have a global, a local, a heap, and a code variable. So then it'll pick one of those to trace through. So that would look like, I'll go ahead and do that. So dash P, what do we want? A global, a local, or heap?
Global.
Global. Okay, so tracing lookup of a pointer, before it goes in, it says this is a value. It's actually f0. In the code, it's f0, but when you make that an integer, it has that extra stuff. And the address of my global variable is this. Okay, so you could now already say what is the page directory entry for this address. First 10 bits. What are the first 10 bits of this address? 0. It's the first 2 bytes, or the first 2 hex digits plus half of the third, and the first 4 hex digits out of that are zeros. All right, and then what's the page table entry row? That's the next 10 bits, which is going to be 2 bits from a 0 plus another 0 and a 1. So it's just going to be a 1. And then the offset into the page is whatever this is as a decimal number. Okay, so let's see. This is from free.c. I print that, and I'm inclined to just give you most of my free.c, but we'll see what you think. So I printed there. This is what I'm passing in, and then I have a system call that I give that address and some flags about what I want it to do. So inside of the system call, it gets the pointer and it prints it. So this was in my user program. This is now in the kernel. That's good that that's the same. I pulled out the directory index is 0, and the page table index is 1, and the offset is that. So that's just looking at this 10 bits, and 12. All right, then I want to pull out this information as well. So to be able to do that, you have to know where the page directory is. So the page directory is somewhere. Any guesses where you look for that? I am saying that my program is at the page directory is here. Or no, that's the actual directory entry itself. I didn't print the address of the page directory. So, all right, we're assuming. So in my other option, we'll print the address of the page directory, but that is in your struct proc. There's a page dir. That's the address of the page directory for this process. Every process has its own page directory. So, and there's something called myproc. Where's it defined? Somewhere. Not that. If you run myproc, it'll return the pointer to your proc. So in your code, you can do something like struct proc p equals myproc, and then you can say p page dir or whatever the name of it was, and then you'd have the page directory, the address of the page directory for the process that's currently running. So that's the starting point. Is you need to get where is this thing located. Okay. right, so we go there. I'm claiming that this is the, suppose this is the actual entry in the page directory. And if you look at this picture, 20 bits are going to be a page number, and then 12 bits are flags, and these are the flags down here. So the 0th bit, the first bit from the right in this 32-bit integer, is the present bit that says whether there actually is even a page where this page number is pointing. What should the present bits be initialized to? Zeros. So the way virtual memory works is you basically set all the present bits to be 0, and then you wait for the process to start using memory. And as it uses memory, you try to go to an address and there's a 0 for present, which means there's no page table there. And then you have to go and create a page table. The kernel has to do that. So this would go under our notes for like virtual memory information somewhere in here. You probably want to keep indenting until it's only like one word per. So this is a, I don't know, a key idea. Page tables are created on the fly or on demand. So you wait for the process to use an address, and when it tries to use an address, it'll have a process has an assembly instruction like, you know, store the value 123 for in address 0x b2af or something like that. So when you go the first time that address is used, there's no page tables. There's just a page directory with only zeros for the present bits. And so then you would find some page directory. So what would the page directory be for this one? Which row? So this would be row 0 in the page directory, right? And then row B, whatever B is. That's 11, right? 11 in page table, offset to AF. So when that happens, on first access, we need to create a new page table for row 0 of the page directory. So we create a new page table. And what do we initialize the present bits to? So now we're going, initially, there's no page tables. There's just a page directory. Now you want to use a memory address, so there has to be a page table. So we go and create, we put the present bit to be 1. We go and create and initialize a page table. What do you set all the present bits to? 0. So we're not going to be using, initially we're not using most of the pages out of a page table. So present bits to 0, but there needs to be one of them that's set. A new page table, set row 11, right? To be a new page we allocate. So we go, there's nothing here. We need to create a new page table, so we create a new page table. We initialize all the present bits to 0, but there's going to be one page we're actually going to use. We go and find a page, and then set this bit to be 1. So the page that we find on some free list is going to say what the physical page number there is. We were over here. Right, looking at flags. In my example here, the page directory is this. So the flags are the last 12 bits. 27 is what? So if this picture is correct, then that page directory entry is present. What's the next bit? Writable. And the next bit, user. So that's good. I'm allowed to access. This was in the free program, some variable that it's using. What about, so what would you expect the writable bit to be for code? If I do, so free-usage, I'm going to say free-p and -code. So that's going to print an address that's from my actual program. Should you be able to change that or not? You could think anything's reasonable, but you could also think as a security precaution, you probably don't want the programs changing themselves. We can see what xv6 does. If we go down to the page table, it's writable. This was printing the virtual, what's the byte that's at, if we look in free, the code one was I took the address of main. So the address of main, the start of my program, happens to have virtual address 0, which is fun and cute. And that is actually in a writable page. Okay, so for this one, what you need to do is you take this address, you, inside the kernel, you're printing out the first 10 bits, the next 10 bits, the last 12 bits, and then you have to go and get your address of your page directory. Then, so your page directory is, let's see, let's take some notes. You guys want some notes? That's not up to date anymore, so let's do this. Okay, so things, useful things. All right, so that's something that you might need to use. You also might want to do right? That's something to get the address of the page directory. Now the page directory is what type of the thing in our C code? It's a pointer. There's this thing is a table. In C, we don't have tables. We have not structure, array. So the page directory is really an array. So once you have the address to the beginning of the page directory, I could say something like PD bracket 12. That's the 12th, row 12 in the page directory. Right, whichever. Right. Okay, so first you need to get the address of where the page directory is, and then once you have that, you can pull out your 10 bits to get a number. And you want to look inside of mmu.h for useful so there's a macro PDX which actually pulls those 10 bits out for you. And there's a macro PTX that pulls out the next 10 bits. So look in mmu.h for PTX, PDX, and other such things to pull out different parts of that. Okay. So then you could get this 20 bits. When we have that 20 bits, then we need to go into the page table. So I could do something like PDET star page table equals PD. If I want to get the 12th one, but I want to get 20 bits, I want to get those 20 bits. So that would be, there's a PTE adder. Then that would be the address of the page table for the 12th row of the page directory. And then that, so that thing is an array as well, right? So if I want to go and get the page table entry, BGT maybe, I don't know, 25 or something like that. Okay. Let me show you the other thing to print. So what you're going to do is you need to make a system call. You know how to make a system call if you finished part A. You need to pass in a pointer that's like part A as well, right? And then you want to start working on just from the top down, and there's two different, right, you need to make all these options work. So you've got the -P, and then there's also the -T, which I actually did the -T first myself. So -T goes through the page directory and looks for all the present entries. And specifically the ones that are less than kern base. Anything that's less than kern base, if you have this diagram memorized, all the ones that are less than kern base, these are memory of the program itself, of the user program. There's the program itself, the text is the program, the instructions, then you have the global variables, stack and heap. So anything the program should ever be doing should be less than kern base. That's these addresses here. So if I just want to look at the memory of my program, that's this stuff. So what this code does, I want to go to the page directory, my page directory, and I want to look through and only the entries here that would be for stuff less than kern base. So which of these entries are for addresses less than kern base? Kern base is let's see, for the -t, print out PDE, PTE information for virtual memory addresses that are less than we want addresses that are less than this. Okay, so what do you, without knowing even where this page directory is or any of the addresses, which of these rows correspond to virtual memory addresses less than that? So that's a question for discussion. Ready, go. Okay, so we want, if we want to look at virtual memory addresses, this thing where it's going to be less than 8 with zeros. So the first part here, the 10 bits need to be less than whatever the, so we want, so that means first 10 bits less than that, right? That's a binary thing. Which, what does that mean in terms of like decimal numbers? You have 10 bits. What's the largest 10-bit number? 1023. 10 bits is like 1,000. So if you're comparing this like decimal numbers, we would want the page directory index, PDX, that pulls out the 10 bits. That's the first one. So we want the PDX of the whatever the address is to be less than 512. That's what this number here, 1 with a bunch of zeros, is 512. That's half of 1,024. Okay, so this, and we're just about out of time. Yippee-doo. Like 6 minutes past. We're having so much fun. We're having, does anybody have to work right now? All right. Good answer. Good answer. All right, so this information here out of the -t is only going to print for the 0 to 511. And you can have that hard-coded or whatever if you want. I was using other methods to pick which ones. But so these are page directory entries that are user code, right? User addresses. So for if there's a page directory entry that has the present bit set, that it's an actual, there's something there, then I have the physical address, or this is the just the raw value of that. That is this thing. So it's an array. The 12th thing in the array, if I just print it as a %x, that's this. And this happened to be the memory address of this, where this row actually was. That's not super important, but I printed it, so what the heck. All right, so then I want to go into that. So here's a page directory entry. Where do I need to go to get that page table? Which bits in the page directory entry give the physical page address? So I'm on this thing. I want the first 20 bits. Everything except for the first 20 bits. So that's this stuff. Okay, so I can set a pointer equal to that address. So I could say something like page table equals, I had page directory bracket, you know, whatever, 12. And then I want to get those 20 bits. And there's a macro for that. PTE adder. So that pulls out the 20 bits that I want. And then I could do page table bracket. What did I have up here? 25. Okay, so in my one that's running here, I would have DFCE as the address of the page table.
DFC 0. That would be 520 bits.
0 DFCE.
You're right.
The last 3 hex digits are the flags. Right. Okay, so I want to go to a page table that's at that location, and then I'm going to go through 0 up to 1024. So I have rows 0, 1, 2, and so on. So I'm looking in this thing, I'm looking at 0, 1, and so on. If I get to one where there's a flag that has the present bit set, then that's actually, right, there's a page. So then I want to just print the page table entry just as something. There's one thing to remember. Well, there's many things to remember, but note, in your kernel code, you need to use virtual memory addresses when accessing the memory. So everybody's supposed to use virtual memory addresses in general, unless you're writing the actual code that allocates the memory. You guys got to go. All right. Well, we're on minute 48. Yeah, right, because you'll be able to just start it at 48. I'm joking. All right. Okay, so in your code, you have to use virtual addresses, but at this point right here, I have a physical address. So I need to turn that back into a virtual address. This is a physical address that's like owned by the kernel. So it's actually pretty easy to convert that into a virtual address. And if you happen to have the figures memorized, so these are virtual addresses here on this side. So if I have a low physical address, the virtual address for that is just with the first bit set. So you just OR in kern base. And there's a macro for that as well. I think it's in mem layout. V to P and P to V. This is for physical addresses. So I would do P to V. Okay, so then I could take this address. I need to P to V it, which basically just sets the first bit to 1. And then that's a virtual address, which is what we're allowed to use. And then go through just like we've been talking about. So I went through this page table. This is one page table that I went through, and I found 12 pages that were present. So I have 12 pages present. Then I have a summary that I went through my page directory The ones that were user addresses, less than current base, I printed this information, but then I have some counts for the other ones as well. So this was user stuff. There was one page directory entry that was there. That's this one. Then the next, I just have this broken into different chunks of memory, just for fun. So between kern base, this is now kernel stuff. The user process wouldn't be able to access this stuff. But in the page directory, there was one page directory entry there. This part here is where the actual physical pages are mapped. So there's 55 there, and whatever, you can see it there. I also printed the bottom of kernel stack. Okay. So let's say that's enough for you to get started.